Okay, Chapter 1, Section 3, Algebraic Expressions. In this section, we're going to be covering adding and subtracting polynomials, multiplying algebraic expressions, special product formulas, factoring common factors, factoring trinomials, special factoring formulas, factoring by grouping terms. So a lot of factoring of polynomials, at least some of the simpler cases. Okay, but first we're going to start with some definitions. So let's start off with the basics. A variable. A variable is a letter that can represent any number from a given set of numbers. If we start with variables such as x, y, and z, and some real numbers, and combine them using addition, subtraction, multiplication, division, powers, roots, some examples of algebraic expressions. Notice that there are no equal signs here. That's a very common mistake early on in algebra. People confuse algebraic expressions with equations, right? So an equation obviously has an equal sign in it. There are no equal signs here. With an equation, your goal is often to solve things. There's nothing to solve here because there's no equation. You could reduce, you can combine, you can cancel, you can expand, you can do different things with algebraic expressions, but you cannot solve anything, right? There's no equal sign to solve anything, okay? Moving on then. A monomial. So a monomial is an expression of the form ax to the power of k, where a is a real number and k is a non-negative integer. A non-negative integer means that it's the positive integers as well as 0. 0 is a non-negative integer, also known as the whole numbers, right? So k is allowed to be maybe 0 or 1 or 2 or 3 or 4, ... And the a is allowed to be any real number, right? Remember, we use this notation symbol to represent real numbers, but in fact we shouldn't have put equal here. It's an element of, right? It's a member of the real numbers. So examples. A real straightforward example would just be the case where we have 3x to the power of 2. Here the role of a is being played by a 3, the role of k is being played by a 2, and the variable is, of course, x. We don't have to use x, we could use any other letter to represent the variable. So maybe, for example, 4y to the power of 7 is another case of a monomial. We could have a negative in front of, in place of the a, any real number. So it could be negative 5, say w to the power of 3. This is allowed, right? We can also have a fraction there. How about 3/4 x to the power of 7, 8, about 8, right? So we can have a negative, we can have a fraction, we can also have a decimal, 3.275 x to the power of 11. We can also have an irrational number. How about pi x to the power of 4, right? So this guy in front, this number out in front, is allowed to be any real number. Positive counting numbers, negatives, fractions, decimals that terminate, and irrational numbers like pi. The exponents, notice that the exponents have to be one of these guys. 0, 1, 2, 3, 4, 5, right? It's got to be a non-negative integer. So, for instance, the 2, the 7, the 3, the 8, the 11, the 4, they're all members of the non-negative integers, right? They're all valued results. Notice that 0 is in there. So that means that something like 5x to the 0 power is still a monomial. And then, of course, we can reduce this because now we know that any value raised to the power of 0 is equal to 1 with only one exception, and that's 0 to the 0. But we're just going to very conveniently ignore that for now and say that this is the same thing as 5 times 1, which equals to 5. So whether you see it as a 5x to the power of 0, 5x to the power of 0, or whether you just see it as 5, either way, this is a monomial, right? So all of these are examples of monomials. Monomial, 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 monomial. So what isn't a monomial? Well, first of all, you have to have a non-negative integer in the exponent. So if we have something like this, 3x to the power of 3.2, that is not a monomial, right? The exponent cannot be a decimal like that. It is a valid mathematical statement. It's an expression. It's valid in math. It's just not a monomial. Or, for example, we could have 5x to the negative 3/4 power, the exponent. And again, a valid mathematical statement. It's just not a monomial. Good. You also can't have something like this. How about 7x to the power of pi? Very interesting expression. But again, you cannot have a irrational number in the exponent for monomials. So all of these are not monomials. Also, by the way, x is a very popular letter to use for the variable, right? As we all know from algebra, very, very popular. Y and z are also pretty popular. But we don't have to stick to those. We could use any letter we want. W, W is very popular. U is very popular. We can also go over to the Greek alphabet and throw some of those letters on there. Alpha, omega, zeta, right? So you'll run into some of those as we move through this class. And it doesn't even have to be a letter, right? It's just a symbol that represents an unknown value. So, instead of having 3x squared, we could have 3 happy face squared, right? Instead of having 4y to the 5th power, we could have 4 small truck to the 7th power, right? It's just some symbol that we're using in place of an unknown value. Good, good. Okay, hopefully that makes sense. So with the definition of monomial in hand, we can move forward now and look at binomials, trinomials, and then in general polynomials, right? So the sum of monomials, the sum of one or more monomials is a polynomial. In particular, if you have a sum of 2 monomials, then you have a binomial. And if you have a sum of 3 monomials, then you have a trinomial. Looks pretty straightforward, right? So examples of binomials could be something like 3x squared plus x. That's a binomial. Or maybe 5x plus 2. That's a binomial. Remember that 2 is the same thing as 5x plus 2x to the 0 power. So to the 1 power, to the 0 power, either way we have 2 monomials. Therefore, we have binomials. Trinomials have 3 terms there. So we could have something like 3x to the 5th power plus 5x to the 7th power plus 4x. That's a trinomial. This is a trinomial in one variable since we're only using the letter x, but we could have a trinomial in several variables. We could have something more complicated like 3xy squared plus 2x 2x to the 3rd power minus 7y to the 4th power. There's an ugly trinomial. Let me stick to them all being addition for now. Good. And then they're all examples of polynomials, right? No matter how many you have, as long as it's an addition of one or more monomials, you'll have yourself a polynomial. Okay, what else did I want to say? Binomial, trinomial. Oh, so the definition says the sum of all of them, right? That's this definition here. The sum of all binomials. So what happens if we have a subtraction going on? What if we have 5x to the 3rd power minus 2x, right? Here we have a subtraction. Is this a polynomial? It is, but we have to use our algebra skills to convert this, or arithmetic skills really, to rewrite this as an addition of a negative 2x, like this. right? We know that adding a negative is the same thing as subtracting its positive. We covered that before. So this is equal to this. These two are equal or equivalent. So when we think about it this way, it is a summation. So when you see this subtraction, it is a monomial. It's just that this is one term and negative 2x is the other monomial, right? 5x to the fifth power is the first monomial, and then negative 2x is the other monomial. So it is the sum of two monomials. Okay, so a polynomial in general, a polynomial in the variable x is an expression of the form a sub n x to the n plus a sub n minus 1 x to the n minus 1, and so on and so forth, dot, 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 all the way down to a sub 1, a to the 1, plus a sub naught, right? The one with a little 0 here is read as a sub naught, where the a sub naught, a sub 1, a sub 2, dot, 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 all the way out to a sub n are the real numbers, and n is a non-negative integer, right? So all these n values are a non-negative integer. I know that this formula could look intimidating the first time you see it, but it doesn't have to be, right? So for example, an example of a polynomial is something like this. How about just 3x to the 7th power plus 2x to the 6th power plus 3x to the 5th power minus 4x to the 4th power minus 3x to the 3rd power plus 8x squared minus 11x to the first power plus 7, right? So here's this really long polynomial. Just to kind of match it up to this thing, this becomes the a sub 7th, right, in there. Notice that this 7 matches with the power, just like here, a sub n, the n matches with that power. This is a sub 6, this is a sub 5, right? So in this little example here, we're letting n equal to 7, right? It's a 7th degree polynomial in one variable. Okay, hopefully that's clear. And then if I wanted to list out the terms, even though that this right here is referring to subtraction, this one's referring to subtraction, and this one's referring to subtraction, then if I wanted to list out the terms, you know, the first monomial is 3x to the 7th, comma. The second monomial is 2x to the 6th. The next monomial is 3x to the 5th. The next monomial is going to be plus negative. So it's going to be negative 4x to the 4th and negative 3x to the 3rd, and then 8x squared, and then negative 11x, and then 7, right? So this is a 7th degree polynomial that's made up of these members. These member monomials are a member of it. Okay, also, it does. You don't have to have every single power represented. So for example, I could have 5x to the 3rd power plus 7, and that's an example of this because this guy is equivalent to 5x to the 3rd power, and then what I could do is kind of insert all the missing powers. So there's this countdown that happens, x to the 3rd plus 0x squared plus 0x to the 1st power plus 7. Back to this guy. Plus 7. Right? So the missing powers of 2 and 1, we can think about inserting them. And as long as we're including a 0 for the coefficient, 0 times anything is 0, so I haven't really changed anything. But now it fits that description exactly, right? This is a 3rd degree polynomial written in one variable, written in the variable x. So this is equivalent to that. So it is a polynomial. Okay, so hopefully that clarifies any issues with polynomials. So here's some more examples, some random examples. Polynomials, right? So here is a polynomial. It happens to be a trinomial. It is written in one variable. By the way, we mostly focus on one variable for now. Every once in a while, you'll have some statement written in more variables, but those are limited cases. Most of the time, we deal with only one variable at a time, which is why for most of you moving on to calculus, you'll see that your calculus class is single variable calculus. We focus just on one variable at a time. Anyway, so this is a polynomial. It also happens to be a trinomial, right? And the member terms of this polynomial are right here. So notice that the difference between here and here is that here we're just listing them, separating them by commas. So this is one monomial, 2x squared. Another monomial, the middle monomial, is negative 3x. Notice that here, this symbol represents subtraction. Here, this is subtraction. Whereas when we're listing the various monomials, this symbol over here represents that it's a negative value, negative. Good. And then finally, the third monomial is just the number 4. Good. Now, it's a degree 2 because the highest power is the 2. That's how we categorize polynomials based on their degree. Okay, here's another example of a binomial. There are 2 terms, one term, the other term, and it's degree 8 because the highest power of our monomials is an 8. Good. Here is another polynomial. Now there's 4 terms, so we usually don't give it a special name, although I've seen some authors call this a quadnomial, kind of staying in tradition with the binomial, trinomial, quadnomial, quintinomial if there's 5, but very quickly those things kind of disappear. So they're not very common, and I don't think this author uses that very much. So binomial, trinomial, and then after that we just call them all polynomials. Okay, so this is a polynomial with 4 terms, 4 monomials, and they're listed out here. Again, notice that this symbol means subtraction. This guy right here means that it's a subtraction. And so does that one. It's a subtraction, right? Minus this quantity. Whereas when we just list out the terms, we come back over here, and now this is representing a negative. Good. And so is this one. This one's a negative. We can always rewrite this as an addition of a negative. Okay, just in case that's still a little confusing. Let me copy it over here. Negative x. Oops. My mistake. I wasn't looking. So here, this is not a subtraction. It is a negative. It's, oh wait, 8 minus, it is. I take that back. So just in case there's a little bit of confusion there, let's expand that. We have 8 minus x plus x to the second power minus 1/2 x to the third power, right? So right now, these little symbols represent subtraction. Subtraction, subtraction for both of those, right? Which is a perfectly fine thing to have. There's nothing wrong with that, except that the definition of a polynomial is the sum of monomials. So this technically right now is not a polynomial, but it is equivalent to one. So we can use our arithmetic skills to rewrite this as an addition of a negative x plus x squared, and then an addition of a negative 1/2 x cubed. So now we've met the technical definition of a polynomial. We have a sum of 4 different terms. 1 term, 2 terms, 3 terms, 4 terms. It's a sum of 4 monomials. Now it's technically a polynomial. So, I mean, it fits the definition clearly. This is also a polynomial because it's equivalent to a polynomial, right? So this is a polynomial. It's just that it doesn't fit the exact definition in its current form. We just use a little bit of arithmetic. We make it equal to something that does, a sum of monomials. And now we have ourselves clearly a polynomial. Okay, so over here, when we're listing the terms of our polynomial, we like to identify them this way. So it's a negative 1/2 x to the third power. Okay. All right. So then we have another example of a binomial, right? Noting again that just having a constant with no variable is a monomial, right? The 1 is a monomial. We can always have 1 is the same thing as 1 times x to the 0 power, right? So it fits that form. And then a single monomial is a polynomial, right? Degree 5 in this case because it's the highest power of our variable. And then again, to reiterate, the whole number, the constant number 6 is a polynomial. It is a monomial. Okay, hopefully those definitions make sense. How do we add and subtract polynomials? The easiest thing we're going to do in this class. Adding and subtracting polynomials, super duper easy. All you have to do is combine like terms, right? So it centers around the idea of distribution. That's one way to think about it. So for instance, if we have to add 5x to the 7th power plus 3x to the 7th power, then what we can think about is sort of the reverse of distribution. We can factor out, right? We're going to get into factoring in a second, but it is the same thing. It's just the reverse of distribution. So this term and this term both have an x to the 7th power in common. So we can set this equal to this, right? Again, it's the reverse of distribution. If we think about distributing like this, going in this direction, we get back to that, right? And so now that we factored out the x to the 7th power, we can see that we can add 5 plus 3, giving you an 8. So there are 8x to the 7th power. Another way to think about this, I think a slightly easier way, is just to note that whatever this is, it is identical to that one. So we have 5 copies of this, whatever this is, plus 3 copies of this, whatever this is. So clearly, together, we must have 8 copies of whatever that is, right? As long as they're identical, we can combine them by adding the constants in front. Good. So we can keep that spirit for anything. If we had 8 copies of a happy face, whatever happy face is, plus 2 copies of that same sad-looking happy face, then together we're going to have 10 copies of that sad-looking happy face, right? Because they're the same thing. 8 copies of this plus 2 copies of that, we have 10 copies of that thing. We can also have 3 copies of a little truck minus 5 copies of that little truck. So together we would have negative 2 copies of that little truck. And it wouldn't make sense if they were combining, right? Like if we had 8 happy faces and we're going to add them with 2 little trucks, it wouldn't make sense to have 10 anything, right? That wouldn't make any sense. So you wouldn't be able to combine them. If these two things are identical, it makes sense that you can add or subtract their constants in front and then keep the same item, whatever it is. But if they're not identical, then it doesn't make any sense to try and combine them in any sort of way. You can't have 10 of anything. There's 8 happy faces, 2 trucks. You don't have 10 happy trucks or something. That doesn't make any sense. Likewise, when we're sticking with variables, if we had 5 of the y's and 3 of the x squares, there's nothing you could do about that. There isn't 8 of anything. This isn't 8yx squared, right? That's not true. It wouldn't make sense to combine them unless they're identical. If they're not identical, you're done. That's as easy as it can get. Okay, so adding and subtracting polynomials is very easy as long as the terms are identical. They have the same powers, the same exponents on those variables. Everything is identical. Then you can combine them by adding their numerical coefficients or subtracting, and then keeping whatever they have in common. Likewise, it wouldn't make sense. Another common mistake is people think that if we combine them, that we raise the powers, right? But again, it wouldn't make sense if you think about this. It wouldn't make sense for someone to say that this is equal to 10 happy face squared, right? That doesn't make sense. I have 8 copies of my happy face, and I'm going to add to it another 2 copies of my happy face. You have 10 copies of this happy face. You wouldn't have 10 happy face squared, right? That also wouldn't make sense. Hopefully that's clear. Okay, so in subtracting polynomials, we have to remember that if a minus sign precedes an expression in parentheses, then the sign of every term within the parentheses is changed, right? So that's because, let's look at this right here. This, well, I'll put it in black. This technically means that we have a -1 times a b plus a c. And now this is distribution of this -1 across this addition. So when we distribute it, we're going to get -1 times b plus -1 times c, right? That's doing this distribution here. -1 times b, -1 times c. Okay, so we're distributing this guy across, so we get -1 times b, -1 times c. And now, using our arithmetic skills, we know that this is equivalent to simply writing minus b minus c, right? Which is what this is. So it's just a quick little reminder that if we have something in parentheses, we have a minus out in front, technically we're going to distribute it across, right? Each one of these terms deserves to be multiplied by that -1. Okay, keeping that in mind, let's move on to an example. Super easy. So we have here this polynomial plus this polynomial. So we have technically the sum of 2 polynomials. That's why we have parentheses around it. But really in this case, we have this polynomial plus this polynomial. But in this instance, that parentheses isn't really necessary. It's not really doing anything. It would be more important to have those parentheses if we had a more complicated situation, like, for instance, if we were going to add 2 copies of this polynomial plus 3 copies of this polynomial, then it would be more important to have those parentheses. But because we don't have that, this is a more easy example. Well, okay, technically there's like a 1 there. 1 copy of this polynomial, 1 copy of this polynomial. We distribute that 1 across. We're going to get 1 times each of these terms. So really we can just remove those parentheses and say that this is just equal to x cubed minus 6x squared plus 2x plus 4 plus x cubed plus 5x squared minus 7x, right? So just equal to that. And now all we have to do is combine like terms. So noting that x cubed and x cubed are like terms, and x squared and x squared are like terms, and x 2x and minus 7x are all like terms. Let's just rewrite it so that they're right next to each other. So we have x cubed plus another x cubed. That takes care of these guys, x cubed, x cubed. And now I'm going to bring together the x squares, so minus 6x squared plus 5x squared. That takes care of this one and that one. And then also I have 2x, so plus 2x minus 7x. That takes care of these two. And then finally, nobody wanted to play with that constant. We can just tack it on at the end, plus 4. Okay, so now these two are like terms. We can bring them together. These two are like terms, keeping in mind there's a minus 6 there. These two are like terms. And finally, we have our constant. Just this once to make sure people are following along. The way I deal with this, and really this, one thing you could do is just convert everything to an addition of a negative, right, using that property. So we have x cubed plus x cubed. Well, that's just going to be 2x cubed, right? To deal with these, I'm going to rewrite it as an addition of a negative 6x squared plus 5x squared plus 2x plus negative 7x plus 4. And now I can combine these. So now I have a negative 6 plus a positive 5. Together they give me a negative 1. So this would be 2x cubed plus negative x squared. And then these two combine, I have a positive 2 plus a negative 7. That gives me a negative 5. So plus negative 5x plus 4. Somebody wanted to play with that 4, we can just attach it at the end there. And then finally we can convert this back again to have 2x cubed minus x squared minus 5x plus 4. Right, so again, let me point out those subtle changes from negatives to subtraction. So here, these guys, this guy is a subtraction symbol, and so is this one. It's a subtraction symbol. And then I converted them using my arithmetic properties to an addition of a negative. So here this is a negative, and here this is a negative. Right? Adding a negative is the same thing as subtracting a positive. Now that I have it in this format, I know what we need to do. We need to have a negative 6 plus 5. That gives me a negative 1. So here this is still a negative symbol. And then positive 2 plus negative 7, that gives me a negative 5. So we have a negative there. And then we go back to our standard notation. We go back to rewriting this as a subtraction. Right? Addition of a negative is equivalent to subtracting a positive. And this one's also a subtraction. Okay, so I know a lot of people skip these steps, and that's fine as long as you have it clear in your head of what you're supposed to do and what the notation means. It's perfectly okay to skip some of these steps. In fact, it's encouraged, right? As you move forward in math, you want to write down enough work to be able to follow, but at the same time, if you put too much work down, then it becomes really dense, right, to follow along. So it's this like Goldilocks balance that you have to find between showing too little work and showing too much work. So that's a little bit up to you. When the exam comes around, of course, if I feel there isn't enough work, then I'll penalize it. But you're always welcome to come back and discuss it with me. If I feel that you definitely knew what you were doing, then I'd be glad to give you the credit back again. But I think at this stage, I would be perfectly okay with you skipping some of these steps. The only reason I really worked it out is because very often a mistake people make is that they see this and this, right? They see minus x squared, minus 6 x squared. Well, I guess I should put the guy in front. So I went through that whole painful explanation because this is a very common mistake. I get x cubed plus x cubed minus 6x squared plus 5x squared, dot, the rest of it. Anyway, this right here is where people often make the biggest mistake. They think that this means to add the 6 and the 5, and they give me negative 11x squared, right? So hopefully I've made it super clear why that's the wrong answer, right? You don't just add the positives and then stick a minus out in front. You can't do that. All right, you guys are beyond that, so you shouldn't make that mistake, right? All right, moving on then. So that one should hopefully be pretty easy. Let's do another one. Oh, here's what the author did. Hopefully they pretty much matched us. Okay, same thing. Here's another example. And this time note that we do have a negative here. Okay, so now we know that this is technically, copy it again, this is x cubed minus 6x squared. And then technically we can rewrite this subtraction as an addition of a negative 1 times x cubed plus 5x squared minus 7x. And then I'm going to distribute. Each one of these terms deserves a chance to be multiplied by that negative 1. So we have x cubed minus 6x squared plus 2x plus 4. Right, so technically there's this 1 that's out in front here, and then it also gets distributed to each one of these terms. So there's a 1 times x cubed, that's this term, 1 times this term, 1. Right? Anytime you multiply by 1, you get that same term. So really, we just get rid of those parentheses for the first term. The next term is the one where we have slightly more interesting things happen. Each one of these terms must be multiplied by the negative 1. So we have plus, I'm going to leave a little space there, x cubed plus a little space 5x squared minus a little bit of space 7x. So I just kept those operational symbols from there, copied it down, but now each one of these terms must be multiplied by negative 1. So we get x cubed minus 6x squared plus 2x plus 4 plus negative x cubed plus negative 5x squared minus negative 7x. Okay, well, we know that subtraction of a negative gives you a positive, so we can simplify that as well. We have x cubed minus 6x squared plus 2x plus 4 plus negative x cubed plus negative 5x squared plus 7x. Good. Okay, so we can combine like terms, and I can see that I have an x cubed there plus a negative x cubed there. So I know that those two are going to cancel. X cubed plus negative x cubed add up to 0. Right? We can also think about this as minus x cubed. So x cubed minus x cubed, that's going to be 0. Okay, so next we also note that this one and this one are like terms. And this is a subtraction of x minus 6x squared. So this is the same thing as a negative. Right? So we can rewrite this as x cubed plus negative 6x squared plus 2x plus 4 plus negative x cubed plus negative 5x squared plus 7x. And so now negative 6x squared plus negative 5x squared, together they give you negative 11x squared, and that takes care of these guys. So we already eliminated that one, that one, that one, and that one. Next, we have this as a like term with that one. So we have 2x and we have plus 7x. Together, we're going to have plus 9x. Plus 9x. And finally, the only one left over is this 4. So plus 4, and that's as good as it gets. Right? No way to simplify that any further. All right, moving on. Let's see what the author do. 9x plus 4. Yep, same thing. So here's what the author did. Same thing. And again, the level of work that you show is really up to you. If you want to take a little time and take some extra steps to make sure you're super clear about the conversions between subtractions and negatives and combining like terms and getting the correct results, that's fine. But highly encourage that you do skip some of these steps as we move forward. Some of this stuff is hopefully really, really basic. All right, adding and subtracting polynomials, super easy. Multiplying algebraic expressions, very easy as well. So to find the product of a polynomial or other algebraic expressions, we need to use the distributive property. So let's say we wanted to multiply this binomial by this binomial. What we could do is think of this as distribution, right? So if we had a plus b multiplied by, I don't know, say y like this, multiplication, one thing we could do is think about distributing these guys. This can be distributed there. This can be distributed there, right? And then we would end up with ay plus by, right? This is distribution of the y across each one of these. I know we're used to seeing it maybe the other way around, ya plus b. Either way, though, we get the same result, right? Y goes there, y goes there, and so we end up with ay plus by. Either way, we get the same thing. And so we're distributing the y across each of these terms. So we end up with the first term times y plus the second term times y. Well, we're doing the same thing here, except that instead of a simple y, we have this binomial. Why not treat it as a little unit and distribute it? So it will be distributed across. So we'll end up with a times this amount plus b times this amount. And that's what this is. It's a times this quantity, a times that, plus b times this quantity. Okay. And then we can do distribution once again. It's kind of like a double distribution method, right? We can distribute there, and we can distribute there. And so we'd end up with a times c plus ad. And then we can distribute here, and then distribute there, and end up with bc plus db, right? I call this the double distribution method for product multiplication. Good. Okay, so just recycling the distribution property over and over can help you multiply polynomials. So that's very popular almost everywhere in the world to do it this way. But Americans, we have our own way of doing things. So we really push something called the FOIL method. The FOIL method, which many of you probably remember, is this. FOIL, right? So what does FOIL stand for? F-O-I-L, right? Stands for the first, the outer, the inner, and last. It's just a mnemonic device. It's just a way to get people to memorize what to do. There's nothing special about the word FOIL in itself. It's just to help you remember this little pattern. And so the pattern, when you're working with a binomial, is this. The F is the first, stands for the first two terms in our binomial. So that would be this guy, F, right? F, which is the A times the C. And then O for the outer is the A times the D. That's the O. The I is the inside ones, so the B times the C. And finally, last is these two. Last, F-O-I-L, FOIL. FOIL is a way of remembering a pattern that exists in order to get the same results. Good. Another way to multiply them is by the table method. So the table method is the following. It kind of mimics the same way you would multiply two numbers, right? If we had to multiply 37 times, 12, we have to multiply that by hand. Hopefully we remember that we would do it this way, like this, multiplication. And then we do 2 times 7, that's 14, 4 carry a 1. 2 times 3 is 6, and 1 makes it a 7. Then we have to introduce that placeholder, and then that makes it a 7, and then that makes it a 3. And then we add down, and then we get a 4. 14 carry a 1, we get a 4. Triple fours, right? So we get that 37 times 12 equals 444. Okay, in that same spirit, if we wanted to multiply A plus B times C plus D, we kind of put them like this, C plus D, and multiply, and you're going to do the same process. We're going to multiply these two together, those two together, those two together, and those two together, right? Just like we did here. These two, these two, these two, these two. So it'll be this one times this one times that one, and then it'll be the C times the B, and then the C times the A. So we get B times D, or DB, the order doesn't matter, keeping in mind that we have to keep track of the signs. So in this case, everything is positive, everything's addition. So then if that changes, just keep that in mind. You have to keep track of that. Then we have AD. And then we don't have this space holder of 0. but we do have to keep in mind that we can only add like terms. So then next we have the C and the B, so plus C and B plus A and C. Good. And then we kind of add them all together, and none of them are like terms, so we're just going to end up with BD or DB plus AD plus CD plus AC. Noting that with addition, we can write them in any order we like, right? So these are all addition. So we can move them around and put them in any order we like. So if we wanted to, we can rearrange them and make them equal to exactly this. So it's just another way of doing it. Again, most of the world likes either the distribution method or the table method. I think very few people outside the US like this FOIL method. So they're all equivalent though. All right, so let's multiply these using the distribution property as well as the table form. So using the distribution property, what we want to do is take this guy and distribute it across those two terms. So let's use the distribution property first. We have 2x plus 3 times x squared minus 5x plus 4. And we're going to distribute this across each one of these terms, this term and that term. So we'll end up with 2x times x squared minus 5x plus 4 plus 3 times x squared minus 5x plus 4. Right, so that's this term and that term. Good. And then we're going to do distribution once again, right? So this is the double distribution method. Like that. And then this guy goes into each of these. Okay, so then this becomes 2x to the third power minus 10x to the second power plus 8x plus 3x squared minus 15x plus 12. Finally, we combine like terms. This guy and this guy are like terms. This guy and, whoa, messed up. No like terms with that guy, right? So this guy and this guy are like terms, keeping in mind that's a minus 10x squared. And then this one and this one are like terms. And then nobody wants to play with the sad cube. And nobody wants to play with the 12. Okay, so that means that we get 2x cubed, and then minus 10 plus 3, that's going to be minus 7x squared. And then positive 8 minus 15 gives you minus 7x plus 12. No more like terms, so that's as far as we can go. Okay, keep in mind that the other thing we could have done, still sticking to the distribution property, is the other way around. We have 2x plus 3 times x squared minus 5x plus 4. The other thing we could have done is thought about this thing as a single unit and then distribute it across. So this times this times this, and then this times that. Good. We get the same answer. So in this situation, we would end up with x squared times 2x plus 3 minus 5x times 2x plus 3 plus 4 times 2x plus 3. And then once again, you do the double distribution property. So now you distribute it again. This times that guy, this times that guy, this times this, making sure to distribute negative 5x. And if you do it, you can keep going. You'll get the same answer as that one after you combine like terms. So either one of those works. And then the other way we could do this is by using the table method. So let's practice the table method. So the other way would be to do this. So we can have x squared minus 5x plus 4, and then 2x plus 3, and we're going to multiply. And just be careful with the notation here. Usually in this style, we like to put a little x here to represent multiplication, but we're also using x as the variable, so that could look a little confusing. So I don't know, little dot, weird. Okay, so we're gonna just multiply. So it's the 3 times that term, 3 times that term, 3 times that term, keeping in mind the signs. And when we're done with all that, it's gonna be 2x times 4, 2x times negative 5x, and finally 2x times x squared. So we're going to have 12 positive plus 12. And then we're going to have these two terms. That's going to be negative 15x. And then these two, which is going to be positive 3x squared. Good. Then 2x times 4 makes it plus positive 8x. And I'm just going to stick it underneath this one since I know that the next step is going to be to combine like terms. So I'm just going to put it underneath that one. So that's going to be negative. So the next one is going to be negative 10x squared. So negative 10x squared. I'm going to put it underneath that one. And finally, we have this 2x cubed. 2x cubed over there. Okay, my last step is to add these. And, well, that'll be plus 12. That'll be minus 7x. That'll be minus 7x squared, and finally 2x cubed. Right? So no matter what, we get the same result. Let's see what the author did. Here's what the author did. Again, the double distribution method, just like I did. So if we have this guy and we distribute it, we'll end up with 2x times this, plus 3 times that. Right. This times this times that. And then again distribute, and that's how you get to this, combine like terms, and we get to the same answer. And then using the table method, same thing. This is a multiplication, so we multiply these, and these, we get this. Looks good. Okay, same thing I did. Special product formulas. Okay, so there exists some common results, some patterns that can be established from some typical multiplications. So for instance, if we multiplied a plus b squared, which is the same thing as a plus b times a plus b, if we applied our good old FOIL method, it's the first, the outer, right? First, outer, inner, and last. And I was a student, like in the 6th grade or something. I remember seeing this for the first time. My teacher introduced this as the red claw method, the lobster claw method. And so you just draw a little claw and it tells you what to do. Right? Just, to me, it just kind of confused me. Like, what does marine biology have to do with math? That's my thought. So, I don't know. Sometimes just memorizing a mnemonic device can do some harm if you don't know where it comes from or why. Any rate, so we have a times a is f. A times b gives me another ab. And then we have another ab. And remember, the order doesn't matter when we're multiplying, so I can just write it as another ab. And finally, I have b squared plus b squared, right? And that's because this is the f, this is the o, this is the I, and this is the L, FOIL. Now, the middle terms are like terms. They both have one copy of A, one copy of B, and there's this sort of invisible one that's out in front, right? One copy of this, one copy of that. So when we combine them, they give me A squared plus 2 copies of AB plus B squared. This is a very, very common pattern. A plus B squared equals that. Right? So I should have copied it here as well. A plus b squared equals this, which equals that. So it's a very, very common pattern, and that's part of our special products. And we come back over here. Here it is. A plus b squared is a squared plus 2ab plus b squared. A minus b squared is another common one. So again, if you FOIL it all out, you see you get the same result. And this one's a very common one. Let's do that one since it's a very, very common one. You have a plus b, and if we multiply it by a minus b, these are called conjugate pairs. They're identical in every way, shape, and form, except one of them has a plus in the middle, addition, and the other one has a subtraction in the middle. Other than that, this part of the polynomial, of the binomial, is identical, and so is this one. Okay, so now when we move forward with our foiling, first, outer, inner, last, F-O-I-L, when we FOIL it, we end up with a squared from the F, and then minus an AB from the O, plus an AB from the I, and then minus a B squared from the L. F-O-I-L. Good. And what happens to the middle terms? They cancel. Right? These guys cancel. These are identical. This is minus AB plus AB. So those two cancel out. And what we have left over is the A squared minus the B squared. Right? So that's the very, very popular special product that we use all the time. A plus B times A minus B is equal to A squared minus B squared. Right? And that's what this is. So this little table gives you several special product formulas. A plus B times A minus B equals to A squared minus B squared. A plus B in parentheses squared is equal to A squared plus 2AB plus B squared. A minus B squared is equal to A squared minus 2AB plus B squared. And these aren't quite as popular, but we still use them quite a bit. A plus B cubed is equal to A squared plus 3A squared B plus 3AB squared plus B cubed. That pattern, you know, it looks a little confusing there. It's really not that bad if you think about it this way. It's A plus B cubed. So the constants out in front come from the following thing, and I think later on in this book we'll cover this, but think about this. I think it's called Pascal's triangle, starting with ones, 1, 1, 1, and then we add this to the bottom, so that becomes that, and then we combine these, so that gives us 2 and a 1, and then we put a 1, and then we add these, and we get a 3, and then we add these, and we get a 3, and then we add a 1, and then we get a 1, and then we add these, we get a 4, add those, we get a 6, add those, we get a 4, and then we get a 1. Right, so we're adding these 2 to get the 2, these 2 to get a 3, these 2 to get a 3, these 2 to get a 4, these 2 to get a 6, these 2 to get a 4. Okay, so it's a nice little pattern, right? Okay, when we're dealing with multiplying these guys, notice the pattern here, let's highlight it. By default, there's a little invisible 1 out in front, so that's like a 1 there, a 2 there, and a 1 there. 1, 1, right? So 1, 2, 1. That's this guy. 1, 2, 1. Good? Because we have a squared, binomial being squared. When we have a binomial being cubed, we go to the next one. See, 1, 3, 3, 1. That's what these terms are going to be. We have this sort of invisible 1 right here. A 1, a 3, and a 1. So we have this guy, this guy, this guy, and then there's a sort of invisible 1 right there. Okay, and the numerical coefficients come from here. So when we want to figure out what this is, a quick little pattern is to know that I know that the first term is just going to be a 1. and then there's going to be something there, plus, and then the next term is going to be a 3, and then there's going to be something there, plus the next term is going to be also a 3, and there's something there, plus, and then there's going to be a 1. Right? So what do we put there? Well, it's going to be AB in every case, AB, 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 right? Because those are the ones we're dealing with. Except what happens is there's going to be a countdown. With starting with the A, we're going to do 3, then a 2, then a 1, then a 0. 3, 2, 1, 0 for the powers of A. And then we kind of go backwards with the powers of B. 3, 2, 1, 0. 3, 2, 1, 0 this way, 3, 2, 1, 0 that way. We know we get our coefficients from this. And now we can simplify it a little bit. 1 times anything, we usually don't write the 1. B to the 0 power is just a 1. So hopefully it's clear that that's just going to be the A cubed. Plus, and now this becomes 3a squared b. This one becomes plus 3ab squared. And this one just becomes plus b cubed, right? And that's how we get this. So that's another very popular multiplication. So it's a nice little pattern to establish. It grows beyond that, right? So if we want to go one more row, this was for the squares. This was for a plus b squared. This one was for a plus b cubed. And if we wanted to deal with a plus b to the 4th power, then we can easily find that out. A plus b to the power of 4. Well, I know the first term is going to be 1 times ab. We'll do the powers in a second. Plus 4 times ab. Plus 6 times ab. Plus 4 times ab. Plus 1 times ab. Right, getting my coefficients from here. Okay. And now we just have to do the powers. So it's a degree 4, so we start with 4. 4, 3, 2, 1, 0. And then we go backwards with the powers of b. 4, 3, 2, 1, 0. And then simplify it. That gives me a to the power of 4 plus 4a cubed b to the power of 1 plus 6a squared b squared plus 4ab cubed plus b to the power of 4. Good. So that's another easy way of figuring out what this is. A plus b to the power of 4. Okay, so you can see that it's not hard to find more powers as we move forward. But what if we have a negative like this one? What do we do then? All you have to do is use our magical powers of converting this from a subtraction to an addition of a negative, and then apply the same rule, and then just keep track of that minus. So for example, a minus b cubed is going to be a plus negative b cubed. And then we follow the same pattern as we did before. It's going to be 1 times a times negative b plus 3 times a times negative b plus 3 times a times negative b plus 1 times a times negative b. And then we raise the powers. So we have power of 3. So all the a's, we start a countdown. A to the 3rd, a to the 2nd, a to the 1st, a to the 0. And then the powers of b, going backwards, we start with 3. That's going to be a 3, a 2, a 1, and a 0. And then we simplify it as best we can. So Any number raised to the power of 0 is going to be 1, even if it's negative. The only exception is when it's 0, so we're just going to conveniently ignore that, because then that would mean this is something different anyway. So this just simplifies to a to the third power. Now, negative b to the power of 1 does not eliminate that minus, so we end up with a minus 3a squared b. And then negative b squared, that does get rid of that minus. So this becomes plus. So we'll end up with a plus 3ab squared. And then having a negative raised to the power of 3 does not get rid of the negative. So we still have a minus b cubed. Right? So there's our way of figuring out what this is. Okay, so there's the other pattern right there. Negative a minus b cubed is equal to a cubed minus 3a squared b plus 3ab squared minus b cubed. Okay, how is this useful? Well, when you're given a binomial like this to multiply, or one of these, you could do it the long way and actually FOIL it out. Or if you remember one of these little shortcut things, you want to do it that way, that's fine too. But what we want to do is be able to just simply use these patterns and apply them to a more complicated statement in a very direct substitution kind of way. So let's look at an example, what I mean by that. If you had to multiply this, so if you're asked to multiply x squared plus y cubed squared, well, that's a lot like dealing with this. Something a plus b squared. And we know that from our shortcut patterns, this is what we get. So when we have a binomial squared, the pattern is that it's the first term squared plus 2 times each of them squared, right? 2 times ab, plus the last term squared. So we can really just substitute the a by this, right? The role of a is this one. The role of b is this one. So that's the b, that's the a. So it's going to be the first term squared. Whatever this is squared, that's this one. The a is being played by an x squared. That's the a. And that's the b. So it's a squared plus 2ab plus b squared. Well, good. So it's going to be this term, whatever it is, squared. Okay, well, in our case, it was x squared, so it's x squared squared. Right? X squared is the a, so it's x squared squared. And then the last term ends up with a b squared, and this guy is the b squared, so we get a y cubed squared. And the middle is twice each of those two terms. The middle is going to be twice the a and twice, times the b. Okay, so we could just apply that pattern and then simplify it. Of course, then we would just take x squared squared. We know we multiply those. We can't simplify that any further. And then we multiply those terms. So we would end up with a final statement that says that x squared plus y cubed squared is equal to x to the fourth power plus 2x squared y to the third power plus y to the sixth power. Okay, so we can just directly substitute and see a pattern, and that hopefully will help us get through some of these in a better way. Okay, so now let's take a look at a couple of examples. Let's say we're asked to find the result of these, multiply these guys. Of course, we could always FOIL them. Let's take number A here. So let's say we have this one. So of course, 3x plus 5 squared is equal to 3x plus 5 times 3x plus 5. So we could go through our regular route of foiling this. This times this, this times that, this times this times that. FOIL, and move forward, and of course we could find the answer that way. But the goal here is to use those special products to establish a pattern. So if we do this, we have 3x plus 5 squared. What we could do is think about this as the A and this as the B in our binomial expansion. So from the table above, we can see that A plus B squared is equal to A squared plus 2AB plus B squared. So just from remembering that pattern, it's the first term, that's the A, it's the first term squared in the beginning, and then at the end, it's the second term squared. Oh, that looks kind of weird here. It's the second term squared at the end here, so plus 5 squared. And in the middle, we have plus 2, and then it's each of them, right? So it's going to be 3x and then 5. So here we have 3x squared. That's the first term squared. And then at the end, we have the last term, the b squared. And in the middle, we have twice the a times the b. So that's the general pattern that's established. All right, so now we just simplify this. This is going to become 9x squared plus 2 times 3 is 6 times 5 is 30. So 30x plus 25. So there we go. So we use the pattern to get to the answer. It's a bit of a shortcut. Maybe not a huge shortcut, but a bit of a shortcut. But more importantly, it'll be useful to know this shortcut in a little bit when we go backwards and factor. In a little bit, we're going to start with things that look like this, and we're asked to go backwards to factor this. And so if we know this pattern, we'll know that this factors as that. Okay, so then the other one is this one. We have, put it over here, we have x squared minus 2 cubed. And again, from our pattern, from our table above, we know that cubed. Right? So you can either have that memorized, or you can derive it like I did a little bit ago, or if you have a nice table somewhere, then you can just get it from there, right? So I'm just simply looking at this pattern right here. A cubed minus 3a squared b plus 3ab squared minus b cubed. Okay, so using that pattern, I can see again, once again, just establishing the pattern, that if this is the A and this is the B, then I can just use that pattern right there to plug it in. So it's going to be the A gets cubed minus 3 times the A gets squared, and then the B plus 3 times the A gets multiplied to the power of 1 times B squared minus the b cubed. So this is the a, so it was the a cubed, and then minus 3 the a squared times the b plus 3 times the a to the power of 1, and then times b squared minus b cubed, and then the b was this 2, and that belongs there, there, and there. So let's just put them in there. So this is going to be x squared, and x squared go there. And then a 2 goes there, a 2 goes there, and a 2 goes there. Right, so I'm using positive 2 because the pattern already has a subtraction. Right, this little symbol right there is a subtraction. And I've already taken that into account when I established this pattern here. And so now this is a subtraction. Therefore, I know that this is a positive 2. Positive 2. Okay, so we put a positive 2 there, positive 2 there, positive 2 there. And now we just simplify this, and that'll be our answer. So we have that x squared minus 2 x squared minus 2 cubed, ends up being x to the power of 6 minus 6x to the power of 4. Then 2 squared becomes 4. 4 times 3 becomes 12. 12x squared minus 8. And so we get to that answer by simply establishing our pattern. All right, moving on. I think the author did it down here. So same thing that the author did. We have the A here and the B here. So it's going to be A squared plus 2AB plus B squared. Right? That's this pattern that appears here. Where this is the A and this is the B. So therefore we end up with A squared plus 2 times A B plus B squared. B squared, A squared. Okay, that pattern's there. And same thing over here, we end up with the same result. All right, moving on. So multiplying is pretty easy, like I said. In this direction, it doesn't seem like a huge shortcut, but in a minute, we're about to talk about factoring polynomials. So going in reverse, these shortcuts can become really, really useful, very often used. Okay, factoring polynomials. Okay, so we use the distributive property to expand algebraic expressions or to multiply. We sometimes need to reverse this process, again using the distributive properties by factoring an expression as a product of simpler ones. So, for example, if we had this multiplication, we saw something like this earlier. This is a binomial times a binomial, right? The operation in between these two by default must be a multiplication. We FOIL this out and expand it, or we can use one of the other methods. Either way, when we multiply this whole thing out, it simplifies to this. So going in this direction, we could say that it's multiplication. So going in this direction is to multiply this direction. And going in the opposite direction, going this way, is what we call factoring. So it's trying to find some way to rewrite this as a multiplication of smaller, simpler polynomials. That's our goal here. Okay, so we say that the x minus 2 and the x plus 2 are factors of x squared minus 4. Good. Okay, so factoring is a really big deal. There's lots of different things to think about. So we're going to cover a few methods to do it. A few of the simpler methods to think about factoring. Number one is factoring terms with common factors. Terms with common factors. So let's say, for example, you're asked to factor a polynomial that looks like this. 3x squared y plus 2xy to the third power plus 5xy. Okay, every single one of these terms has an x in common, at least, well, exactly one x in common. This one has two x's. This term only has one x. And, well, this term also only has one x. So all three terms have an x in common. So what we can do is factor out the x, right? It's sort of the reverse of distribution. So what I want to do is rewrite this like this. I want to rewrite the original polynomial as a multiplication of x times something such that when I do distribution, I get back to the original, thereby saying that this new product is equal to the original. So x times what equals this? Well, we'd end up with a 3, of course, to get that constant. And there's still one more copy of x and a y. So x times 3xy equals to 3x squared y. X times 2y cubed gives you 2xy cubed. And finally, x times 5y gives you 5xy. Okay, so this is sort of the reversive distribution. If I distribute this x across each of these, if I multiply this times this times that, and this times that, I would get back to the original. Okay, but now we're not done yet. There's still one more value, one more variable that they all share in common, one more factor. They all have 1y. So we can factor that out, and so we'd end up with an xy, and then the first term would end up with 3x, plus the second term we'd end up with a 2y squared, plus the last term would just be a 5, right? Again, this is the reversive distribution. If I was going to multiply this term times the first one, I would end up with this. So xy times 3x gives you 3x squared y, and xy times 2y squared gives you 2xy cubed. And finally, xy times 5 gives you 5xy. Okay, so we can say that this is equal to this. So let me copy it over here. 3x squared y plus 2xy cubed plus 5xy is in fact equal to this, and there's nothing else in common by all three terms, so that's as simple as it gets. We can't factor it any further. Okay, so that's the principle or the idea behind factoring a polynomial that has common factors. Let's do a couple of other examples. Notice that in this case, they both share both a factor of 3 and a factor of x. So for this one, I'm going to say that 3x squared minus 6x is equal to, they both have a common factor of 3x, and then there is one more x that goes there. 3x times x gives you 3x squared, minus a 2. If we multiply 3x times 2, we get minus 6x. And that's as far as we can go. What about this one, part B here? What do they have in common? So looking at the coefficients, we have an 8, we have a 6, and we have a 2. So they all share a common factor of 2. The least common factor between those three terms is a 2. And then the x's, they all have one x in common, and they all have two y's in common. Good. So I'm going to factor out a 2xy squared from all three terms, and then I have to figure out what goes here. So there's three pieces here. So I want to figure out what goes here such that this term, if I was going to do the distribution, this times this term should be equal to the first one. So I can see that blank times 2 equals 8. That's got to be a 4. And then blank times x equals x to the 4th power. That must be x to the 3rd power. And, well, the y squared times 1 equals y squared. So that's it for that term. Next, I got to figure out what goes in the middle here. So blank times this must be equal to this middle term. So 2 times something equals to 6. It must be a 3. And then x to the power of 3. This must have an x squared in there. X times x squared equals to x cubed. And then there must be a y in there. Y to the power of 2 times y to the power of 1 gives me y to the power of 3. Minus, then 2, okay, that's a 1 there. And so for this last term, it's just going to be y squared. Right? So it's really just a guessing and checking kind of thing. Try something, think about it, and figure out what belongs in these blank spots so that when I distribute them, they give me the same result. So I can just kind of pretty that up a little bit and conclude that 8x to the 4th power y squared plus 6x to the 3rd power y cubed minus 2xy to the 4th power must be equal to 2xy squared times 4x cubed plus 3x squared y minus y squared. Okay, here's another example. A little trickier. First thoughts, first instinct might be to start foiling this guy out and working with the results, and that might lead to the right answer, but it would be a lot more work. Instead, notice that if we had this, let's say for a second, let's say I had this, 2x plus 4 times, say, w minus 5 times w. If I had this, it would make sense that I can factor out the w, right? W is common there, w is common there. I can factor that out, put a w out here, and then what would be left over would be a 2x plus 4 minus a 5. Right? The distribution process here, if I distributed w times this first term, I would get this, right? This whole term would be equal to w times this one, and then w times the 5 would give you this term. That term becomes that. Good. Now that I have that, then I can simplify this by saying that I still have this w out here, and inside the parentheses, I could just rewrite this as 2x plus 4 minus 5. So I got rid of these parentheses because they're not really doing anything. This set of parentheses here, this one and this one, is really indicating that there's one copy of that polynomial. So 1 times that, distribute it, well, you could just get rid of the parentheses, right? Okay, and then finally we can combine those two and say that this is equal to w times 2x minus 1. Okay, we want to do the same thing, except that instead of a simple w there, we have this more complicated thing, x minus 3. But we can still treat it the same way. Here is my w. Here is my w. So I want to factor that out, put it on the outside. So we're going to put a x minus 3 out here. And then there will be parentheses. And then there's this 2x plus 4 minus a 5, parentheses, equals, okay, so it's this whole thing here. So then it's x minus 3 times, and then I end up with a 2x minus 1. Good. And then we could do, we can either do FOIL or we can do distribution again. And so let's try that. I'm going to think about the fact that I'm going to distribute this whole thing. That whole thing gets multiplied by that one, and that whole thing gets multiplied by that one. So I'll end up with 2x times x minus 3 minus 1 times x minus 3. One times x minus 3. So let's highlight that. So it's this whole thing times the first term, this whole thing times the next term. And then we're going to do distribution once again, right? So it's the double distribution method. I'm going to distribute these two, and then distribute this and distribute that, keeping in mind that this is subtraction, so we can rewrite it as an addition of a negative 1. So I'm going to rewrite this as a plus negative 1 and distribute that. And so I end up with 2x times x gives me 2x squared. 2x squared minus 6x minus x plus 3. Good. Now the middle two terms combine to give me my final answer of 2x squared minus 7x plus 3. And that's my final result. Okay, so that's the first type of factoring. Keep an eye out for situations where you can factor out a common factor. Often we'll be dealing with more straightforward cases like something like this, where you can factor out a constant and maybe a couple variables. But sometimes we get some really tricky things like this where there's a common equation to a couple of terms and we can factor that out. Okay, the next type of factoring that we're going to do is factor by grouping. Factor by grouping will come about in situations where we run into this. So consider the following. If we had x plus y being multiplied by a plus b, and we do our, let's go back to our FOIL, this times this times that, this times this times that, we FOIL it all out, we'll end up with xa plus xb plus ay plus yb. Okay, so now if we're asked to factor this, to go in reverse, our first thought is there a common factor to all the terms? And there isn't. There isn't a single variable common to all four terms. The first two terms have an x in common, and the last two terms have a y in common. These two terms have an a in common, and these two terms have a b in common, right? So there's a lot of commonalities all over the place, but and these two had an x in common, and these two have a y in common, but there isn't a single letter that's common to all four. So we can't use the technique of step number one, factor on a common factor, but we can use this factor by grouping. And what we want to do is come up with the way to reverse this process. So instead of foiling, we're going to do it the other way around now. So remember, the other way around to do this is the double distribution method. You had x plus y times a plus b. So if I do the double distribution method, I'll end up with a times x plus y plus b times x plus y. And then I'll distribute the a again. I get ax plus ay plus bx plus by. The reverse of this, to undo this, what we're going to do is we're going to factor by grouping. We're going to focus just on the first two terms and recognize that they both have that a in common. That'll allow us to go from this step to that step. And then we're going to allow ourselves to reverse this from this to this. And then finally, we're going to go backwards and do that. Okay, in order to do all that, I'm going to write down some steps, and then we'll do an example and see how those steps help us. Okay, so factor by grouping. Number one, note that this is only going to be valid as long as we have 4 terms or 6 terms or 8 terms and da 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 da. Right? Only da 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 da. Right? So it could be 8 terms, it could be, right? So it's got to be an even number of terms starting at 4 or more. In practicality, that makes it nice because it's easy to spot them. Almost always we'll be dealing with ones with 4 terms. 6 terms, 8 terms, 10 terms. Those are too difficult. We usually don't run into crazy things like that. For us, almost always, it's going to be 4 terms. So if you run into something that has 4 terms and they ask you to factor it, this is probably how you're going to do it. Factor by grouping. Okay, so we're going to have 4 terms. So what we're going to do is step number 1. We're going to I like to underline the first 2 terms. Okay, number 2, factor the first 2 terms. Factor the first 2 terms. Okay, I will go through the list of instructions and then we'll do a problem and we'll see how these steps translate. Once you factor the first 2 terms, number 3, you're going to put a plus blank. So write a plus number Number 4, include a blank space. Include a blank space. Number 5, copy the binomial from step 2. And finally, fill in the blank. Fill in the blank with a value that creates a true statement. I'll show you what I mean by that. Okay, so let's jump into an example, and then we'll see how each one of these steps will help us get there. So let's say, for example, we're asked to factor this guy. Okay, so like I said, my first idea is to underline it. Do not throw parentheses in there because you might be messing with the signs. So don't include parentheses at this point. But underline it. Focus on the first two terms. What do they have in common? So step number 1 is to underline it. Step number 2 is to factor the first two terms. So let's factor it. They both have an x squared in common. So we have x squared out here, and then that results in an x plus 1. Okay, so that's what I mean by step 1 and step 2. Underline it, and then step 2 is to factor the first two terms. Step 3 is to include a plus sign. Step 4 is to include a blank space. And the next step is to copy the binomial from step 2. That's this guy. Copy it down. Write it down exactly the way you see it, including the signs, everything identical. And then finally, the last step is to fill in the blank in order to make a true statement. It must be true that the product of these two must be equal to the last two terms. So blank times x must be equal to 4x, and blank times 1 must be equal to 4. So a little guessing and checking lets me know that that must be a 4. Okay, so I want to fill in the blank such that I get a true statement. The product of the last, a distribution of the last terms is equal to the last two terms of the original polynomial. So fill in the blank with a value that creates a true statement. The distribution. Okay, so fill in the blank with a value that creates a true statement. The distribution of the blank value, the one you're looking for, and the binomial must be equal to the last two terms of the original polynomial, as we see in this case. And finally, when you're done with that, last step is to factor the resulting binomials. By design, these two have to be identical so we can factor them out. That's why we copied it. Back in step 5, copy the binomials from step 2. These two have to be identical. So now, because this binomial and this binomial are identical, we can factor them out. And that would result in x plus 1 times x squared plus 4. Okay, so we've managed to factor out this polynomial into the product of two simpler polynomials, such that if I FOIL these out, I get back to that original value. Okay, so those are the instructions. Underline the first two terms, factor the first two terms, write a plus sign, include a blank space, copy the binomial from step number 2, fill in the blank of the with a value that creates a true statement. It must be true that when you multiply that blank value times the binomial, that equals to the last two terms of the polynomial, the original polynomial. And finally, the last step is to factor out that common binomial that will result. If this doesn't work out, by the way, you might want to come back over here and switch around some of these terms. Like maybe the way it's originally written won't work, but maybe if we switch around the order of these, we might find some other way in which it works. All right. So here's what the author did. Okay, same thing. Let's try one more example. All right, so following my steps. Let's underline the first two terms, try and focus. Well, I guess, by the way, the order in which I'm presenting these is the order in which I think you should do them. So the first thing you should do when you're asked to factor a polynomial is think if they have any common factors, right? They don't have a common factor to all four of them. The first three terms have a common factor of x, but there isn't a single factor common to all four of them. So that's the first technique. It failed. There are four terms, so it makes me think that maybe this factor by grouping will work. So I'm going to underline the first two terms. They both share an x squared in common, so I'm going to write down an x squared times an x minus 2. That's what they have in common. I'm going to put a plus sign, a blank, and then copy this. A common mistake people make is that they start trying to be too smart for their own good. They jump into trying to factor this thing, and sometimes that leads to issues. So I would say follow the steps, factor the first two, put a plus sign, put a blank, copy this binomial exactly the way you see it there, and now try and fill in the blank. Blank times x must be equal to minus 9x. Pay attention to the sign. And blank times negative 2 minus 2 equals to plus 18. So a little bit of guessing and checking. You can see that negative 9 is the one that works. Negative 9 times x equals to negative x. And negative 9 times negative 2 is going to be equal to positive 18. So we end up with x squared x minus 2 plus negative 9 x minus 2. Okay, so now if we just simply recognize that these two binomials can be factored out, we can pull that out in front. It's the reverse of distribution. And so we end up with x squared plus a negative 9, this is a 9, which then becomes x minus 2 times x squared minus 9. And then that leads to the next way that we're going to factor things by noticing patterns. So if you already noticed this pattern, you know that this is going to be x squared x minus 2 times x plus 3 times x minus 3, right? And then that's going to lead to the next technique of factoring by noting that there's a pattern. This comes from knowing from earlier that if we have this pattern, a minus b, a plus b, and we FOIL this whole thing out, oops, this guy times this guy times that guy, this guy times that guy, we FOIL it all out, we end up with a squared plus ab minus ab plus b squared, oops, sorry, minus b squared, minus b squared, and then the middle terms cancel out, so we're just left with a squared minus b squared. Good, so that's one of the patterns that we know. Also we know, well, okay, so this is just one of the patterns that we know. So we know that if we want to go backwards, if we end up running in a situation where we have something squared minus something squared, we know that if we want to factor it, it'll be equal to something that fits this pattern. Good, and that's what we have here. Something squared minus something squared. So we have x squared minus 9. That's the same thing as x squared minus 3 squared. We have something squared minus something squared. Therefore, following this pattern, I know that it can break down into x minus 3, x plus 3. This is here where the a is equal to that. That's the a. And so we have a, and then the b is equal to this 3, b squared. And so that equals this. Right, so just following that pattern along. So this is what the author did. And then that leads to the special factoring formulas. So as I just mentioned, we have one pattern already established. And then another pattern, well, here are all the patterns. that we've already been working with. So we already saw this exact same table above when we were looking at multiplication. We just saw it in reverse. When we wanted to multiply these two, we did FOIL, 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 and we saw that it equaled this. When we wanted to multiply this binomial, we would expand it all out, do FOIL, 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 and they would end up with this. So now we just want to go backwards. And what we especially want to do is note that when we run into something that fits one of these patterns, that we know that it factors this way. So one of the most popular ones being this difference of squares. This one. Whenever you run into something that it's something squared minus something squared, we know it factors this way. Okay, so for example, let's say we wanted to factor this guy. Okay, the first thing we'd note is, do they have anything in common? No common factors? No, none at all. Do they, can we do factor by grouping? Well, there's only 3 terms. Remember, factor by grouping requires 4. So no, not that. So the next thing you try is to see if it fits one of our patterns. So can I rewrite this as something squared? Yeah, it's x squared. Can I rewrite the last term as something squared? Yep, it's 3 squared. Is it true that the middle is twice the 2 values that you squared? X and a 3. And it just so happens that it's true. So this happens to fit the mold of a plus b squared equals to a squared plus 2ab plus b squared. It fits that pattern, where the a is this guy, and the b is this guy and this guy. Right? Here is this guy is a, this guy is a, this guy is the b, and this guy is the b. It just so happens to fit that pattern. So because it fits that pattern, I can easily conclude that this must be equal to the a, which is an x, plus the b, which is a 3, squared. A, b, squared. The a and the b squared. Okay, let's keep going. What about this guy? So again, you want to ask yourself, is it true that I can write the first term as something squared? And yeah, that's 2x squared. Is it true that I can write the last term as something squared? Well, yeah, it's the y squared plus. Okay, is it true that the middle is minus 2 times the 2 things that you were squaring? That's a 2x, yeah, and that's a y. Yeah, that's going to be true. So it fits the pattern where this is the a, this is the a, this is the a, and then this is the b, and this is the b. So it fits the pattern of a minus b squared equals a squared minus 2ab plus b squared. So from that, I can conclude that this must be equal to 2x minus y squared, right? Just because it fits that pattern. Note that this method only works in cases where the original polynomial just happens to fit a very nice pattern. If it didn't fit that pattern, then we wouldn't be able to use this method. We would try something else, or maybe it just doesn't factor. And it's actually really easy to mess up the whole thing, even by one value. If the original one was 4x squared minus xy plus y squared, just the fact that the 4 is gone, well, then it doesn't fit this pattern, right? I need there to be a 4 there, and it's not there, so it doesn't fit the pattern. I wouldn't be able to factor it this way. Maybe I try something else, but maybe it just doesn't factor. Good. Or if maybe just one of these exponents was off. If instead of a 2 there, this was a 3, simple little thing like that, oh well. Even if this 4 was there, oh well, it doesn't factor this way. It only happens to fit that form, so I can use it. If it doesn't fit the form, then we're out of luck. Try something else. Okay, so here's another one. Let's try this one. So again, we have potentially difference of squares. So we have 3 to the 3rd power is 27. x to the third power minus, and then we can also rewrite this as 1 to the third power. So we could rewrite this as 3x to the power of 3 minus 1 to the power of 3. So let's look at our table here. Difference of cubes. Difference of cubes is equal to this. Okay, so we can just use this formula. Notice that when we have a subtraction there, we have a subtraction there, and then this pattern over here. Notice also that this one looks an awful lot like this one, except it's missing the 2. Right? So it's not quite the same. This one here has this 2 right there, whereas this one is missing the 2. There's no 2 there. So it's very similar, but not quite the same. So we copy it here. We have that a minus b, a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. Okay, so just following along with that pattern, I can see that this is going to be equal to a minus b, so that's going to be the 3x minus the 1 times the a squared, so that's going to be 3x squared plus 3x times 1 plus the 1 squared. Right, just following along with that pattern. Here is the a, so the a becomes a minus the b, a gets squared, and then plus ab, and then this guy is the b, and it's a minus b times a squared plus ab, so here's the b, plus b squared. So just following along in that pattern, I can see that this factors as the product of these two, and now I can just simplify it and say that 27x to the third power minus 1 is equal to 3x minus 1 times 9x squared plus 3x plus 1. Right, so it looks like you did something really amazing when really you're just following this little pattern here. You can amaze your friends by memorizing a simple little pattern and finding a way to factor it, right? So our goal was to come up with a multiplication of two polynomials that are smaller than the original one, such that when you multiply them all out, we get to that. So let's check. Let's come over here and check it. I'll put it in blue. Check. Let's make sure it works. If it's going to work, that means that when I FOIL this, I'll get something that equals that. So foiling it, I'll end up with 27x to the third power. So far, so good. And when we multiply this and that, and then this times this, and then this times that, is going to give me plus 9x squared plus 3x. And then I'm going to distribute this guy, minus 1, minus 1, minus 1, times all of these guys. So I'll end up with negative, so minus 9x squared, these two. And then minus 3x, and then minus 1, minus 1. The middle terms cancel out. These guys cancel, these guys cancel. And all I'm left with is 27x cubed minus 1, which is exactly what we wanted, right? So it worked out. All right, next one. Again, I can see that has something to do with powers of 3. I can rewrite this as the following. X to the 6th power plus 8 is equal to x to the 2nd power to the power of 3 plus 2 to the power of 3. So it has something to do with powers of 3. And so the sum of something cubed plus something cubed, going back to my little patterns over here, something cubed plus something cubed equals to x plus b and then I have this little pattern right here. Notice that when this is a minus, we end up with a minus there and a plus there. And when this is a plus, we get a plus there and a minus there. So just a little pattern to remember. So let me write it down over here. We have that a cubed plus b cubed is equal to a plus b times a squared minus ab plus b squared. So just following along that little pattern, I can see that the first term is going to be equal to x squared plus 2 times x squared squared minus x squared times 2 plus x squared. I'm sorry, 2 squared. So that's x to the 6th plus 8. So x to the 6th plus 8 is going to be equal to x squared plus 2 times x to the 4th power minus 2x squared plus 4. And again, we can FOIL that all out, and we can see that we're going to get the same answer. Right, moving on. Factor completely. So sometimes we might have to apply different techniques to get the whole thing out. So the first thing I notice is, let's see, we could factor out a 2x squared. Let's see how that helps us out. So if we factor out a 2x squared, we end up with x squared minus 4. And now we see that this is one of our patterns. This is something squared minus something squared. I can rewrite this as 2x squared, x squared minus 2 squared. And so this is like the first technique. Factor out a common factor. They both share a 2. They both share an x squared. Factor that out. And now this is one of our simple patterns, a difference of squares. So following along with my pattern, I know that this will be equal to minus 2. And so that's as simple as it gets. So we have to use 2 different techniques. Okay, let's try another one. Again, let's factor out what they have in common first. They both share 1 copy of x, and they both share 2 copies of y. So the first thing I can say is that this factors by pulling out an x, pulling out a y squared, and what results is x to the power of 4, and then the y got factored out. And then I factored out the x, so minus y to the power of 4. X to the power of 4 minus y to the power of 4. Okay, well, we don't really have a formula for the difference of 2 terms being raised to the power of 4. But we can rewrite it this way. It could be something squared minus something squared. So we're back to our difference of squares, right? So that's where the a is this guy, and the b is this guy. So we're back to difference of squares. So this is going to be xy squared times, it's going to be this squared plus this squared. And then next we have this squared minus this squared. Right? Following along the pattern that a squared minus b squared equals to a plus b a minus b, like that, except that instead of a simple a, we had an x squared. So it becomes a there and a there. And instead of a simple b, we have this b, this b, this b there. That would be this one. So this was the b, and this one was the a. So it's this squared minus this squared, means that it's the sum of these two in the binomial, and then the difference of these two in the binomial. We're almost there. There's no way to break this down any further, but then this becomes the same pattern one more time. Deja vu. So then our last and final answer is going to be that we have this term, x squared plus y squared, And then this one becomes x plus y times x minus y. This becomes x to the fifth, y squared minus x, y to the sixth power. All right, so keep an eye out for our patterns. So it can be very useful to memorize that little formula of patterns. This guy right here, to give you some of the more popular ones. There are other ones, more complicated ones, but I don't think most people expect you to have those other more complicated ones memorized. But I think you are kind of expected to have these 5 memorized. So there you go. So far we have 3 ideas. When you're asked to factor something, number 1, look to see if they have a common factor. Number 2, think about factor by grouping. Number 3, check to see if one of our special formulas works. If none of those things work, we move on to our 4th type of factoring technique. And the 4th type of factoring technique is to factor a trinomial of the form x squared plus bx plus c. Now, in order to do this guy, consider the following. Consider what happens when we do a typical binomial product like this. So consider what happens when we have x plus 2 times x plus 5. Let's say that. Okay, we foil it along, foil, foil, and we end up with x squared. This times this is x. And then we end up with 5x plus 2x plus 2 times 5. I'll leave it as 2 times 5 for now. The middle terms will add, combine like terms, so we'll end up with x squared plus 7x plus 7x plus, and then in this case we get a 10. Okay, so let me copy this over here. X plus 2 times x plus 5 equals to this. So again, a lot of math is all about just patterns. So if we think about the relationship, the connection between this number and this number and this number and this number, notice that they multiply to give you that 10 and they add up to give you that 7, right? We can see why that is. As we FOIL, the last step is to multiply the 2 times the 5, so we're going to get that 10. And then with the middle part come from combining like terms, which is going to end up being the sum of these two. This only works as long as we have a 1 in front of the x here and the 1 in front of an x here. Because if it was something more complicated, if we had a number in front of the x, when we FOILed it, we wouldn't have such a straightforward pattern with the rest of it, right? This would get a little more complicated, and so would that. So in the simple case where we end up with a polynomial like this, there's a 1 in front of here. There's no other constant, just an invisible 1 there. The variable x squared plus some constant x plus some constant. Whenever we have this pattern, then I can tell that the answer is going to fit this pattern. Let's do it one more time with just letters. So let's say we have just the x plus an a, and then the x plus a b. Again, when we FOIL it, we'll end up with x squared plus bx plus ax plus ab. This is the f. It's that f guy. This is the outer. This is the o. It's the o. This is the I. This is the I. And then finally, our last, L. There's our FOIL. And again, these two terms are like terms, so we can combine these two. They both share a common factor of x. They're like terms. So we can just combine their two numbers. We add the a and the b. So this becomes x squared plus ab, so a plus b, x, order doesn't matter, plus an a, b. Good? All right, so if we focus on something like this, we have x plus a times x plus b, we end up with this. And so what we want to establish is, again, that relationship that exists between this, this, and this, and this, right? In this situation where we have a polynomial that fits this form, notice that we have the x squared, and there's an invisible 1 out in front. If there's something else there, it would make it more complicated, but it's an invisible 1, x squared, plus some number there, x, plus some other number there. And it must be true that the addition of those two equals the summation of those two, and the product of those two is this product is the multiplication of those two. Good. Okay, so here's what we're saying. Oh, author did the same thing here. Okay, that's exactly the same thing I'm saying. So let's just jump into an example. Let's say we want to factor these guys. Okay, it fits our pattern, right? So we want to say that whenever you want to factor anything that fits the form a, b, x plus c, anything that fits this form, the answer is going to be x plus blank times x plus blank, right? And it'll just be your mission to figure out what those blanks are. But as we just established, those blanks must be two numbers such that when you multiply them, they give you the C, and when you add them, they give you the B. So just for the sake of notation, let's say that I refer to them as P and Q. I'm looking for P and Q. Find P and Q, and there's two conditions. It must be true, so I'll put such that when I multiply the P times the Q, P times Q, it's got to be equal to that constant C. But when I add the P plus the Q, it must be equal to the B, right? Those are the two conditions. And so it just becomes kind of a guessing and checking situation, but hopefully not too bad. Okay, so in this case, it fits the pattern. Here, there is a 1 out in the front. That's what we wanted. X squared. So we're only dealing with quadratics here. Power of 2, x squared, plus a constant. Okay, so this guy is the role of b. So for us, b equals 7. And then the c is equal to 12. Okay, so because it fits that pattern, I know that x squared plus 7x plus 12 must be equal to x plus blank times x plus blank. Keeping in mind those blanks could be negative, maybe one or both might be negative, or maybe none. Now my role is to find them, find those two blanks. And instead of calling them blank number 1 and blank number 2, I'll just call it the p blank 1 and the q blank 1. Those two values, I got to find them, find p and q. And I know from my patterns that it must be true that P times Q is equal to the 12. And it must be true that when I add them, they add up to the 7. But at the same time, it must be true that P plus Q is equal to 7. Okay, and now it's just a guessing and checking situation. What numbers multiply to 12 but add to 7? So you just got to, rely on your awesome algebra arithmetic skills to think about the products of 12. So it could be 12 times 1, but then if I add them, that's like 13. That's not going to work. It could be 2 and 6. 2 times 6 works. Yeah, that gives you 12. But if I add them, that gives me 8. And then 4 and 3. Right? 4 times 3, that'll work. They add up to 7. So I found them. Just kind of guessing and checking, I figured out that it must be true that this is the case. X squared plus 7x plus 12 must be equal to x plus 4 times x plus 3. right? And then you just kind of guess and check. That's going to be x squared. That's going to give me a 3x. That's going to give me a 4x. That gives me the 7x. Oops. This guy doesn't get a squared. There. Combining the middle terms will give me the 7x plus, and then 3 times 4 is 12. So there we go. We factored it. Okay. Be careful that it fits this pattern. If it doesn't fit this pattern, you can't do this. For example, if this had been x cubed plus 7x plus 12, good luck. Do it some other way. It doesn't work this way. This is only valid for things that fit this form. X squared plus blank x plus blank, right? It has to fit that form. Now, we could change the variable. That's just a dummy variable. So we could have y squared plus 7y plus 12, and that's okay. We have essentially the same question, just a different variable. So that will still work. But it's important for things to work out this way. Now, someone might ask, well, what if one of these numbers was off? Instead of a 7 there, what if this was a 2? Find two numbers that multiply to 12 but add up to 2. That probably isn't going to work, right? You can think of different scenarios, right? So it's very easy to come up with one that doesn't work. If it doesn't work, it doesn't work. Try something else, but this method isn't going to work. Okay. Another thing is this technique right now is only valid when the coefficient has a positive 1 there, or nothing. By default, if nothing's there, then there's a 1. If there's something else there, then it might not work. So if we have x squared plus 7x plus 12, but there happens to be like a 5 there, well, this method isn't going to work. We're going to try something else. That's the last thing that's the last technique we're going to look at, but it quite possibly won't work. And it definitely won't fit this pattern, right? This pattern is only valid as long as it fits this very rigid form of a binomial, of a quadratic, sorry. Okay, let's try. Okay, so that's the solution. Let's factor one more. Okay, it fits the pattern. We have something, we have x squared plus bx plus c, right? So we have something squared minus a constant x minus the other value of c. So for us, this is the role of b. The role of b is equal to a -2. Be careful with the signs. And the role of c is being played by a -3. So if it works, if we can find a way to get this thing to factor, it must be the case that this is going to be equal to x plus blank times x plus blank. And I know that those two blanks, whatever they may be, say p and q, it must be true that p times q is equal to -3, and that p plus q must be equal to -2. And so now comes the guessing and checking. What two numbers multiply to -3 but add to -2? So kind of think through it. -3, so it could be like -3 times 1. Oh, I got it right off the top there. They multiply to -3, but they add the -2, right? Other possible candidates could have been the other way around. +3 times -1. They multiply to -3, but they add to +2. So that's definitely not it. And there really weren't too many other options. So this guy's it. All right, so then we just plug it in and double check to make sure that we got the right answer. Must be equal to x minus 3, x plus 1. Right, and then just FOIL it just to double check. We have x squared. We have positive x minus 3x. That's going to give me the -2x minus 3. So yep, we got it. What about this one? Okay, it looks really tricky to begin with, but we could do sort of a combination of things. We can think about that as a little unit, right? Think of that as the following. What if we had w squared minus 2 times w minus 3? if we had this pattern here, then it would fit the pattern from above. So this, if it's going to factor, would factor into w plus blank times w, times w plus blank, and it must be the case that these two numbers multiply to the -3, but they add to the -2. Now, we already did that. That's going to be equal to -3 and +1. They multiply to -3 and they add to -2. Or, again, simplifying it, would be w minus 3 and w plus 1. Okay, that's how we would factor it. Okay, but in this case, we have something a little bit more complicated. So we can think of doing a substitution. Let w equal 5a plus 1. And once we do that substitution, then we have that exact same pattern, w squared minus 2 times w minus 3. Right? We've already done that work right there, so we know that this equals to w minus 3 times w plus 1. And next, we have to go back and resubstitute the value of w. W, let's put it in red actually. The w was this guy. So the w is 5a plus 1. And there's a 5a plus 1 there. And then there's a minus 3. And then there's a plus 1. Good. Okay, so now we can simplify that. And our final answer would be 5a minus 2 and a 5a plus 2. Okay, and that's as good as it gets. Can't go any further. Here's what the author did. Same thing, noting that there's a pattern that is established there. Blank squared minus 2 times blank minus 3. So we can do a w substitution. That blank could be thought of as the little binomial of 5a plus 1. And we end up with the same answer. All right, the last thing we're going to tackle is the most complicated one. And that's cases where we have a trinomial of the form ax squared plus bx plus c. So this is presumably where the a is not equal to 0. This is where a does not equal to 0, because if it was equal to 0, then this whole term would be 0, and then we'd end up with something much easier to factor. So we're just going to ignore the 0 case just because it would make life way too easy. And we're also going to ignore the case where it's a 1, because if the a was a 1, then we would be back in the case number 4, right? They would be the simpler case. So this is going to be a much more complicated situation. I'll write down the instructions for this, and then we'll do an example, and we'll see how you would solve it. So in order to factor these guys, I'm going to do something called the AC method. The AC method. Okay, well, the AC method means that step number 1 is we're going to take that A, and we're going to take that C, and we're going to multiply them. Step number 1, multiply A times C. Step number 2, it's going to be very similar to before. Our goal is going to be to find two numbers. Step number 2, find two numbers. P and Q. P, Q, such that, now in step number 4, or the fourth technique, We wanted PQ such that they multiplied to C and they added to B. So we're going to do something very similar. We want to find two numbers such that when you multiply these two numbers, PQ, they equal AC. The answer to step 1. And at the same time, though, we want those two numbers, PQ, to add up. Oops. We want those two numbers to add, to sum up to the value of B. Okay? So very similar to step number 4, or technique number 4. PQ must be equal to AC, but at the same time, I want them to add up to the B. Once you find those two numbers, if they exist, and this is the hard part, finding these two numbers, but if you can find those two numbers, if they exist, we move on to step number 3. In the previous technique, once you found those two guys, you were kind of done, right? If you know, in technique number 4, we had things that look like this, x squared plus bx plus c, and I said that if we can find those two numbers, then we'd be done. The answer would be x plus blank, x plus blank, and then we would put in our p and our q there, and we wanted those two numbers to multiply to c, and those two numbers to multiply to b. But in our case, because we have a slightly more complicated situation, we're not done when we find the p and the q. The next thing we're going to do is we're going to replace the b with p plus q. Replace b with p plus q. P plus q in the original polynomial. In the original polynomial. In the original polynomial. Okay, what does that do? Well, we're allowed to do that because of this step, right? That's the whole point of finding these two numbers, p plus q. They're two numbers such that when you add them, they equal the b. So we can come in here and replace this b with a p plus a q and replace it and put it in there. And once you've done that, what you have done is found a way to separate the middle term, right? We're going to distribute that x and we're going to separate that middle term into two terms, thereby giving you 4 terms. And now the last step is going to be to factor by grouping, right? So distribute the middle terms, separate the middle terms. And 5, factor by grouping. Factor by grouping. By grouping. This whole process is not easy. That's why I saved it for last. So not only did we tackle 5 unique techniques for factoring a polynomial, but I did them in the order that you should think about them, from the thing that will solve it the easiest, finding a common factor. That's the easiest thing you could do. Number 2, factor by grouping. Do that. Number 3, look at our patterns, see if it fits one of our established products of polynomials. Number 4, if it's one of the easier trinomials that has a 1 in front of the x squared, then it'll be like this one over here. Then it'll be like this. Right? If there's a nice, pretty 1 out in front. And if there isn't a 1 there, something more complicated, then we're going to have to do it this way. Okay? So let's try one out, and we'll come back and see how these steps play in. Okay, chapter 1, section 3, number 74 asks us to factor this guy. Okay, so we go through our 5 factoring techniques. Number 1, do they have anything in common? Any factors in common? None at all, right? These two terms have an x in common, but this one doesn't have an x, and there are no constants in common. Nothing we can do with the first factoring technique. Factoring technique number 2, factor by grouping. Can we use that? Nope. We need 4 terms minimum, and there's only 3 here. That won't work. Does it fit one of our patterns? We want to ask. Okay, if it fits one of our patterns, it should be the case that the first term can be rewritten as something squared. It's not going to be easy. We could fudge it, as you'll see in some later examples. We could try to rewrite this as the square root of 5x squared. That'll give me that, something squared. The last term, again, we could do the same little trick and say that this is root of 6 squared, I guess. But it's not true that the middle is twice the two things that you're trying to factor, right? So that's not going to be true. That's going to be the root of 30, and that's not 7. And also, there's an extra x in there. And also, we have a minus here and a minus there, and none of our patterns fit that, right? If this fit a pattern, it would be one of the ones that would look like this. I mean, we might be hoping for this one. But this one turns into this. Something squared, something squared. The middle term happens to be twice the two terms that you're squaring, and there's a subtraction there. Well, this fails from the very beginning just because that's a minus, and this has a plus. So right off the bat, I should have known that it's not going to fit one of my patterns. Okay, so that's not going to work out. Let's get rid of that. So we move on. The next thing we think about is, does it fit the form x squared plus bx plus c? If it fit that form, that would be the easier case where I know the answer looks like this, where I just need to fill out those two blanks such that it gives me that answer. Not quite. Okay, so this fits the last form where we have the AC method, right? This fits the form ax squared plus bx plus c, and that's where the b is being played by a -7, and the c is being played by a -6, right? So we're going to do the AC method. AC method. The AC method says that, number one, let's multiply the a and the c. So that'll be equal to 5. Oops, I forgot to mention here. The a is being played by a 5. Right? This is the a, okay? This is the b, and this is the c. So the AC method. So step number one is to multiply a times c. A times c is going to be equal to 5 times -6, which equals to -30. Okay, that's the first step. Step number 2 is to find two numbers p and q such that they multiply to the AC. So find p and q such that p times q is equal to -30. But at the same time, when you add them, at the same time, p plus q should be equal to the c. P should be equal to the b, so it should be equal to -7, right? So they multiply to the product of AC, but they add up to that middle value, which happens to be a -7. Okay, this is the hard part, guessing and checking different ways to do that. So we can think of numbers that multiply to -30. So we can think of, obviously, 5 and -6 would work. But if we think about the addition, 5 plus -6, they add up to -1, so that doesn't work. And we can flip around the sign, -5 times 6, that's also going to work as a product, but it's not going to work in terms of the addition. So 10 and 3 will work. So if we do -10 times +3, we end up with -30. And -10 plus +3 add up to -7. So that will work out. And now I can come back over here and go to step number 3. Now step number 3 says to go back to the original polynomial, this guy here, and replace that middle term with the sum of the p and the q, which is this, right? So this is what we want to use. So now we want to go back to the original polynomial, 5x squared minus 7x minus 6, and we want to replace this minus 7 with this. Now, just to be real clear about this, this is equal to, let's change it to addition again. This is going to be 5x squared plus negative 7x minus 6. So that means I'm going to replace this minus 7 with minus 10 plus 3. So this will be equal to 5x squared plus, and then I'll put it in, let's put it in red. Let's put it in blue. We'll get a negative 10 plus a 3. Negative 10 plus a 3 is equal to negative 7. And then that is being multiplied by x, and we have this minus 6. Okay, then we distribute this x, and we end up with 5x squared minus 10x plus 3x minus 6. Okay, well, just doing it once or twice, you see that you don't have to go through all this trouble. It's pretty easy to see that when you find these two numbers, it's minus 10x plus 3, x gives you, adds up to 7x. Minus 10x plus 3x equals negative 7x. So we could have just replaced this whole thing for the minus 7x, whatever pattern you see. Okay, so that's the next step. Replace that middle term. Let me write down these steps. We had step 1, step 2. Step 1, multiply the a times the c. Step 2, find two numbers p and q such that they multiply to the ac, but they add up to the b value. We have that. Step number 3 is this one, to replace the middle terms. Replace that middle term. And finally, step number 4 is going to be to do factor by grouping on this. Step number 4 is going to be to factor by grouping. So we have 5x squared minus 10x plus 3x minus 6. So remember, factor by grouping, underline the first two terms. What do they have in common? They have a 5 and an x in common, so let's factor that out. 5x, and that results in an x minus a 2 plus blank copy, and that copy is going to be x minus 2. And now fill in the blank, right, such that blank times x equals to 3x, blank times minus 2 equals to minus 6. So I think a little guessing and checking lets you know it must be a 3. 3 times x equals to 3x, and 3 times negative 2 equals to minus 6. Good. Okay, so now the next step in factor by grouping is to factor out the common binomial. So this one and this one get factored out. And we end up with, I'll put it over here. We end up with x minus 2 times 5x plus 3. And that's it. That's our final answer. So here is our final result. Also notice that I think very popular to all of this, I know you've had other teachers, another very popular way to do this is simply the guessing and checking method. And that often works as long as the numbers are relatively easy, and usually they give you fairly easy numbers, so things work out. But the AC method is a nice, concrete, systematic way of solving things that always works. Well, always works as long as there's a nice whole number solution. But this way, the other way that people do it, is to just simply do blank x plus blank, and then blank x plus blank. And then they're just trying to figure out these two numbers. These four numbers. Two numbers that go there, two numbers that go there, two numbers that go there. Right? They're just trying to fill in those blanks. And it's usually not that hard because it must be true that when we do our FOIL method, this term times this term this term times this term has to be equal to the initial term. So there's not that many ways that can happen. Really, there's only one way, and in the current case, being a 5 there and a 1 there, or the other way around, a 1 there and a 5 there. So let's try that. So the other way could be that there's a 1 there, or the other way around is could be that there's a 1 there and there's a 5 there. Okay, and then we also know that the product of the last two, we know that the product of these last two must be equal to this constant over here. So there's not that many options there either. For instance, it could be a 1 and a 6. And of course, we have to think about signs. So it could be a 1 and a -6. It could be a -1 and a +6, right? Those are the kind of options that can go into that last one. Or it could be a 2 and a 3, a 2 and a 3, where maybe the 3 is negative and the 2 is positive, or the other way around. The 2 is negative and the 3 is positive. So there's really not that many options available. Right? In fact, here, let me organize it in a slightly different way. I made it kind of ugly, didn't I? So everything I said can be organized in the following way. Plus blank plus blank. Okay. So in these blanks, we can either put a 1 and a 6, sorry, and a 5, because they have to multiply to this +5 here, or the other way around. It could be a 5 and a 1. Or we can also think about the fact that they could be negative, so maybe they're both -1 and -5. So those are all the options that can go for this blank that's missing out in front here. So you kind of have to pick and choose which one is going to fit. And then for this last term, the multiplication of those two must be 6. So there's only a few options there as well. It must be equal to -6. So it could be -1 and +6. It could be +1 and -6. It could be a 2 and a -3, or it could be a -2 and a +3. And we can see through all those combinations that we would end up with this option as well. So -2 and +3, that's this one, -2 and +3, combined with a 1 and a 5. So 1, 5, and then -2 and +3. That's the pattern that works. This one and this one is this one, and then this one and this one gives you that one. So that's the other guessing and checking method that people learn. Just try different things until something works out. That is often also organized through this sort of a diamond method, like this, where they think of two numbers that will work out. We want them to multiply. Just kind of guess and check your way for them to multiply to +5, but then they need to add the -6. And then you just kind of guess and check your way through different things. And the hope is that eventually you run into the numbers that work out. Right? The diamond method. Okay, so any way you learned it is fine, as long as you get to your final answer. And if none of this works, keep in mind that maybe the thing doesn't factor, right? There's plenty of polynomials that just don't factor. They're already as reduced as they can get, right? They're called prime polynomials because they can't go any further. Or it might be something that does factor, but it doesn't factor by one of these 5 techniques. You need something more sophisticated to be able to factor it. And we'll be covering a more interesting approach later in the book, right, that can deal with more complicated cases. All right, so that should be good enough for you to be able to do the homework in this section. As usual, let me know if you have any problems.